Hello everyone, let's continue our discussion on analyzing the curves that we got from the last video. So in the last video we took a CMOS inverter and simulated it against various supply voltages, and we observed by the first observation it says that your CMOS inverter is even able to operate at a voltage as low as 0.5 volts. Okay, so why not use the 0.5 volts? And again, I'll show you some significant advantages of using 0.5 volts, but there are again reasons why we don't go for a 0.5 volt operation. So let's try to look into some of them. So we'll start with a gain factor. We'll start with the first factor, that is the gain. So let us try to identify how much gain do we get by operating your CMOS inverter at a voltage of 2.5 volts, at a supply of 2.5 volts, versus same CMOS inverter being operated at a voltage of 0.5 volts. Okay, so if you want to calculate the gain, you just need to go back to your curves. The gain is basically a change in the output voltage by change in the input voltage. It's a ratio of change in output voltage by change in input voltage. So if you see that, if you see from this curve to this curve, if there's a small change in the output voltage from this point, if you tap this point and if you tap this point, there is a small change in the input voltage that leads into significant change in the output voltage. So that is your gain factor. Okay, so for this particular curve, if you want to calculate the gain factor, you just need to click on this point somewhere over here. Okay, so you'll get a value of x0 as 1.05645 volts and y0 as 2.08 something, and then next you click on this particular point where you see where you see a slope of -1. So this is the point, and you get this particular value 1.31855, and y0 is y0 is 0.333, and so on. So, and in order to calculate the gain, you need to subtract this minus this, you need to subtract this minus this, and take the ratio of this one. So it basically says change in the output voltage divided by the change in the input voltage. That's basically your gain factor. So that's what we have done. We have already done that for this particular curve, and the gain that we get for this curve is about 7.38. Okay, so this is the gain value that we get for the curve, which is for a CMOS inverter which is operating at 2.5 volts. On the other hand, if you try to look into this tiny curve which is present over here, for a small change in the input voltage, you see a huge change in the output voltage. Okay, so this particular curve looks to be sharper than the curve that you see over here, and as a result of that, this is expected to give us pretty huge gain. Okay, and we did that as well. We calculated the gain for this one also, and the gain value is about 11.53. So this is a very huge increase in the gain. It's about 56% improvement in the gain of these two between the same CMOS inverter, just being operated at two different voltage levels. So what is the disadvantage of not using the CMOS inverter with a supply voltage of 0.5 volts? I'll come back to that in some time from now. Okay, but there are definitely some advantages for using this particular CMOS inverter, or basically using a CMOS inverter by lowering the supply voltage and using a CMOS inverter by a higher supply voltage. There is definitely an advantage of using this, but there are again disadvantages as well in using this particular curve rather than this one. So we'll first note down the advantages of using 0.5 supply volts, and it's you see an increase in the gain close to 50% improvement. Okay, and that's a very big gain factor, that basically a small change in the input voltage can lead into bigger amplification. So that's a pretty good advantage for an analog designer. Okay, let's move on. Let's look into another factor. We call it as energy. So if you have this CMOS inverter on your mobile phones, how much energy will that CMOS inverter consume while you have two kinds of CMOS inverter? Let's say you have this inverter and this inverter. This inverter operates at 0.5 volts and the same inverter operates at 2.5 volts. So how much energy is getting consumed? And the energy is basically half CV square. So coming to the concept of energy, half CV square is lost into power dissipation, and half of the energy is being consumed while transferring from logic 1 to logic 0. And I'll talk about energy a lot when we go into the dynamic simulations for your CMOS inverter. So let's take this formula right away from here. Energy is half CV square, and V is the voltage and C is the output load capacitance, the capacitance that this inverter is trying to charge or discharge. Okay, that's about a brief introduction to energy, and we'll talk a lot about power dissipation and energy in a separate course. So the energy that is being consumed by a CMOS inverter that is operating at 2.5 volts is half CV square. So basically energy is proportional to a value of 2.5 square. So there is some, let's say if these are constant, your energy is 2.5 square multiplied by some constant. On the other hand, if you operate the same CMOS inverter at a lower voltage, at 0.5 voltage, your energy is half C into 0.5 square. Okay, and that's a very significant improvement or reduction in the energy, and that's about 96% reduction in energy reduction. So if you just subtract this 2.5 square minus 0.5 square and see the gain in the energy, that is about 96% energy reduction. So why not use this kind of CMOS inverter, or why not use an CMOS inverter that operates at lower voltage? Again, there are disadvantages and we'll talk about that. Let's note the second advantage that we see using a 0.5 volt supply, and that's significant reduction in energy, and that is close to 90%. We saw 96% improvement, but I'm just stating a term which is close to 90%. Okay, so what can go wrong? We have increase in the gain. We have about 50% improvement in the gain, which is a very good factor for an analog designer. We have significant reduction in energy, which is close to 90% improvement. So you can save a lot of power in your batteries, in your mobile phones or your watches. So what's wrong with this one? Why can't we use this kind of power supply for a mobile chipsets or something like that? Let's look into some of the disadvantages of this one. If you calculate the rise delay and the fall delay for a CMOS inverter which is biased or which has a supply voltage of 2.5 volts, you'll get the value of rise delay and fall delay. You will, first of all, the curves will look something like this. If it's basically we have simulated, we have done the spice simulation for getting the rise and the fall delay in the past videos. You might want to have a look into them. So the rise delay that we get and the fall delay that we get for a CMOS inverter which is simulated at 2.5 volts is 66 picoseconds and 78 picoseconds respectively. Okay, but as soon as you reduce your supply voltage, to 0.5 volts and keeping all the elements as constant, if you will very soon observe that for charging the same output capacitance, this supply is not enough. Okay, and if you do the spice simulation for a VDD which is 0.5 volts, this is what the output that you get. So if this is your input pulse, this is your output pulse. So if you see over here, the device is not even able to charge or completely discharge the load capacitance, because this voltage, the amount of voltage that we have, that is 0.5 volts, is not, the rise time is not sufficient enough to charge your output load capacitance to 0.5 volts, and that's a major disadvantage. It's an impact in the performance of your device. So your device might not even operate, your device might not even be as fast you expect it to be. It might go slow. So if I increase the time period to, let's say, even more, you will be able to see a rise and fall, discharging and charging capacitance, but it needs time. So a device which is operating at 0.5 volts needs some extra amount of time to perform the same actions that was performed by a device which is operating at 2.5 volts. Okay, so when you have a 2.5 volts, you need a small rise time. You have enough room for your output load capacitance to charge. You have enough supply available to charge an output load capacitance. It's as good as a water tank which is like 10 liters and a water tank which is of 1 liter. You have only a liter of water to charge your output capacitance, and you have a 2.5 liters of you have 10 liters of tank that is readily available with you to fill up a tank of to fill up your output capacitance. That's the basic difference, and this will be our prime topic of discussions in our next course, which will be uploaded over here. So let's try to identify some real simulations over here. So let's say we'll not operate your device as 0.5 volts, but we'll operate your device at 1 volt. Okay, in that case you will see the curves are compared to the curves those were at 2.5 volts. There is a huge difference over here. So it takes time for your output capacitance to get loaded over here. Okay, in contrast to the curves that you see in the previous case where it was operating at 2.5 volts, the rise time, the rise delay was different, was smaller enough compared to the one that you see for this one, for a device that is operating at 1 volts. And this is our prime discussion for our next course. If you see, the rise delay is 220 picosecond and the fall delay is 165 picosecond, and that's a performance impact. That's a huge performance impact, and this will be our prime topic of discussion in the next course, in the next course of circuit design and spice simulation, where we will be talking only about dynamic simulations. And I'll explain the exact reason behind the increase in the rise time or the decrease in the rise time with the change in voltage. Okay, so that will be our that will be the prime topic of discussion in the next course. So though we have an advantage of increase in the gain when we do a static simulation, we have increase in the gain, we have a significant reduction in energy, but with that said, there is a significant impact in the performance. Okay, and we'll try to explain this one in our next course. So from the next video onwards, we'll look into another topic like device variation. We'll vary the CMOS inverter device size in such a fashion and try to simulate the device in with respect to standard inputs, and see how does the device variation impact the behavior of the CMOS. Okay, so CMOS inverter should be intact in its behavior while we vary the device. There will be different sources of variation that will be explaining you, and how does CMOS inverter is robust or immune to the device variation. So let's try to look into all this from the next video. Thank you.